It is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through exact values and obtuse angles. This relates to trigonometry and is only a 10A topic. So you don't need to watch this if you're not doing the 10A stuff. So some trigonometric ratios, when they have the right angle, have an exact value. So we'll see in a second, for example, sine 30 has an exact value. I'll show you what they are and why they are what they are. So let's look at a right-angled triangle, which is what we've been doing. Now, it turns out that if this angle here is double this angle, there are special things about the ratio. So if that angle is double this angle, the only possibility is that this is 60 degrees and this is 30 degrees, right? So in a triangle such as this, where the angles are 30, 90, 60, it turns out that the shorter side is half the longer side. So the hypotenuse and the shorter side are in the ratio 2 to 1. Now, the shorter side of a triangle is always, in any triangle, it's always opposite the smallest angle, So if this is the smallest angle, this will be the shorter side. I'll call it A. So if the hypotenuse is double that length, it will be 2A. Okay, A can be any number. So what about this side here that I've marked with an X? We can figure that out using Pythagoras. So X would be square root of C squared minus B squared. Okay, remember the formula for Pythagoras, you minus when you're finding a shorter side. So it's the square root of 2A squared gives us this. They are like terms, so I can add them up. Okay, now I can simplify this into root 3 times A. So this side X will be root 3 times the shorter side. So root 3 is like 1.73, blah, blah, blah. So if you have a triangle that's 30, 60, 90, then the shorter side is half of the longer side, and the other side is about 1.73 times the shorter side. So we can easily figure out the values of sine 30 and sine 60 and so on. So sine 30, so we're talking about this angle here, is opposite over hypotenuse. The A's cancel out and we get a half. Sine 30 is equal to a half. Sine 60, so sine of this angle, opposite over hypotenuse. So it'll be root 3A over 2A. A's cancel out. I'm left with root 3 on 2, which is about 0.8666. Okay? So we can do the same for the other ratios. So tan of 30. So again, we're looking at this angle here, is opposite over adjacent. So it's A over root 3A, or 1 over root 3. In the same way, tan 60, you can try this for yourself, will be root 3. Cos 30 is the same as sine 60, and cos 60 is the same as sine 30. Okay, I'll put these in a table for you at the end of the video. So I just want you to be aware that's why we have the exact values that we do. Okay, now I'm going to show you another special case. That's when we have a right-angled isosceles triangle. So if I have a right-angled isosceles triangle, obviously the hypotenuse is the longest side, it's the other two sides that are equal. So when you have two sides of a triangle equal, you also have two angles equal. So this angle must be 45 and 45. Again, I'll call this A. This one here must also be A. To find the third side, the hypotenuse, I use Pythagoras. This time I add them together in the square root because I'm finding the longest side. So A squared plus A squared is 2A squared. It's just root 2 times A. So when you have an isosceles right-angled triangle, the hypotenuse is root 2 or 1.41 blah 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 times as long as each of the shorter sides. So this hypotenuse is root 2a. So we can figure out the ratios really easy. Sine 45, it doesn't matter which of the 45s you use, is opposite over hypotenuse, a's cancel out, I'm left with 1 on root 2. It's about 0.707. Cos 45 would be exactly the same. Adjacent over hypotenuse, a's cancel out. So tan of 45 would be just a over a. That makes sense, because when you have a 45-degree angle in a right-angled triangle, it's an isosceles triangle. The opposite and adjacent are equal. That's why tan 45 is 1. So the other exact values you need to know are 0 and 90. So to do that, I'm sort of cheating a bit. I'm saying what happens to sine, cos, and tan as the angles get closer to 90 or to 0. So let's say we have a right-angled triangle like this. So we always have a right angle. Now, if another angle is very close to 90 degrees, then you're going to have a situation like this. Okay. So this angle here is large, as in close to 90. This angle here is small, right? So what would be the value of sine, cos, and tan? Well, let's call this angle theta and this alpha. So alpha is large, theta is small. So let's look at theta. So when theta is small and close to 0, you can see the opposite side has to be very small compared to the hypotenuse. So it's close to 0. Tan of this angle, the opposite is a lot smaller than the adjacent. So tan theta will be very small and close to 0. But cos theta, when the angle is very small, you can see that the adjacent side, which is this one here, is almost the same length as the hypotenuse. So cos theta is approximately 1. Now, if we look at a large angle, alpha, the opposite happens. So sine of alpha, now this side is the opposite, and it's very close in length to the hypotenuse. So when you have opposite over hypotenuse and they're similar in length, it'll be about 1. So we have tan of alpha. So we can see that now tan, which is the opposite over the adjacent, the opposite is way, way, way larger than the adjacent. So tan can get as big as it likes. As the angle gets closer and closer to 90 degrees, tan just gets larger. And cos alpha, well, now this side is the adjacent. It's very small compared to the hypotenuse. So when you have adjacent over hypotenuse, the adjacent's very small, the hypotenuse is large. If you have a very small number divided by a very large number, then that will be close to 0. So from this, we now get a table of exact values. So here, I said that alpha is about 90 and theta is about 0, and that will go into our table, putting all this together. So this is the table of exact values. So hopefully what you notice is as theta is increasing, as it gets closer to 90 degrees, sine theta approaches and gets closer and closer to 1. This is as theta gets closer to 90 degrees. As theta gets closer to 90 degrees, cos theta approaches 0. But as theta gets closer to 90 degrees, tan theta just gets bigger and bigger. Remember, sine theta and cos theta the ratios, they are ratio of opposite to hypotenuse and adjacent to hypotenuse. Sine theta and cos theta must always be less than 1, because you can't have the opposite or the adjacent being longer than the hypotenuse. But tan can get larger and larger because the opposite can be much larger than the adjacent. There's nothing wrong with that, okay? So these are the exact values that you will need to know. So now we're going to look at obtuse angles. So let's say I want to find the value of sine theta, cos theta, or tan theta, where theta is obtuse. It's more than 90 degrees and less than 180. So let's say, for argument's sake, I want to find the value of cos 150, sine 150, and tan 150. So it's a little confusing because we can't have a 150 degree angle inside a right-angled triangle. That doesn't make any sense. So what we'll do is we'll label this the x-axis and the y-axis. And I'm going to look at the angle made with the positive x-axis. So if I want to draw a 150-degree angle, I could draw a line here. Okay? So this angle here, let's say it's 150 degrees. Now this circle, we're going to make a unit circle. So it's going to be a circle in the Cartesian plane, center origin, and it's going to have a radius of 1. So you've graphed circles like that before. Okay, so if the radius is 1, then the length of this line here is 1. So if the angle I marked there is 150 degrees, then the angle here would be 30 degrees because they add up to 180. So I'm going to make a right-angled triangle here. Okay? So if I wanted to find just cos 30, I could draw a triangle like this. And I'll call this angle, I'll say this angle here was 30 degrees, right? So this length here is 1. The reason it's 1 is because the circle has radius 1. So the distance from here to here is whatever the x value is. So if the x value here was like root 3 on 2, that would be the distance. The distance from here to here is y. So cos of this angle 30, it would be adjacent over hypotenuse. It'd just be the x value, whatever that x value is. Sine of 30 is opposite, which is y over 1. Y over 1 is just y. Tan 30 will be whatever the y value was, the opposite over the adjacent, which is whatever the x value is, right? So cos of the angle, cos theta is the x coordinate, sine theta is the y coordinate, and tan theta is y over x. And that's how we're going to define cos 150, sine 150, and tan 150. So if this angle made with the positive x-axis is 150, then we have the blue line here. The cos of that angle is just the x value. So again, the x value here is going to be the same as the x value here because the distances are the same, except it will be negative. So cos 150 gives you the same as cos 30, except now it's negative. The x value is negative because cos of theta was the x value. So sine of 150, so sine of this angle here is the y value. So the y value here and here, if the angles are the same, the two y values would be the same. Sorry about my poor drawing, but they would be the same. So sine 150 would be exactly the same as sine 30. And tan of 150... well, that is the y value over the x value. Now, the y value is still positive in this quadrant. All the y values are positive, but the x value is negative. So it will be negative tan 30. This is just an explanation of how we come up with some important rules in trigonometry. So sine of 180 minus theta is the same as sine theta. We can generalize this. Whatever angle you make here, if you make the same angle on the opposite side, the two y values will be equal. Sine theta is just the y value. So then cos of 180 minus theta gives you the same value as cos theta except negative. And similarly, tan of 180 minus theta is negative tan theta. Okay, so these are three important rules. This is how we define sine, cos, and tan of angles that are obtuse. So let's say I wanted to find what is the value of sine 120. So we subtract 120 from 180, we get 60. So sine 20 will be the same as sine 60. Now we know that sine 60 from previous slides is equal to root 3 on 2. So sine of 120 we've now defined. Let's say I wanted to figure out what is cos of 135. So 180 minus 135 is 45. So cos 135 and cos 45 have the same value, except the obtuse angle is negative. So cos 135 will be minus 1 on root 2. If I, say, wanted to find the value of, let's say, tan 150. So 180 minus 150 is 30. So tan 30 and tan 150 have the same value, except the obtuse angle here will be negative. So tan 30 was 1 on root 3, so tan 150 will be minus 1 on root 3. So that's how you find exact values for obtuse angles. So I'm just going to draw the table again and this time update it. So this was our table before, and I'm now going to add in the obtuse angles. So sine 120 is the same as sine 60. Sine 135 is the same as sine 45. Sine 150 is the same as sine 30. And sine 180 is the same as sine 0. So we'll now do for cos. So cos of 120 is the same as cos of 60, but it's negative. The x value is negative in that quadrant. And similarly for the rest of them. So these are ways you can work out the exact values for obtuse angles. We'll do tan now. So tan 120 is the same as tan 60 except negative. Tan 135 is the same as tan 45 except negative, and so on. Okay, so try and understand and learn these table of values. I know this is a very difficult concept to get. Please let me know if you need any help. This has been the luckiest maths teacher in the world. Have a great day.